All right, let's do another example with relative velocity. In this one, we have an airplane that's going to be flying in the wind. And at the end of the video, I'm going to show you this solution visualized clearly and color-coded so that it's easy for you to understand. But in the meantime, I'm going to walk through this solution step by step. So the question asks, a pilot wishes to reach a destination that is directly to the north. There's a wind blowing at 210 kilometers per hour at an angle of south 65 degrees east, and the plane can fly at 515 kilometers per hour in still air. What will be the plane's heading? So this is asking what will be the plane's direction. So the first step with problems such as this is I want to draw a diagram. So given the information that we know, we're going to draw a little sketch. It's not going to be anything fancy, but it's going to help us to visualize what the question's asking. So we have a destination. Actually, before I go any further, I'm going to draw our directions, north, east, south, and west. So we have our reference point. So we have a destination, and a pilot is wishing to reach that destination that's directly north. So we're going to have an airplane somewhere down here flying to reach the destination. Now, what else do we know to draw this sketch more accurately? Well, there's a wind that's blowing 210 kilometers per hour south 65 east. So let's look on here, south 65 east. So we're going to go south and then 65 degrees towards the east. It's going to be about here. It's going to be some arrow like this, and if this is 65 degrees, we know that 90 minus 65 is equal to 25. So this here is going to be 25 degrees. So let's draw that vector here. So we're going to have some vector. We're going to have some vector that looks kind of like this. We know this is going to be a 25-degree angle, right? Okay. And we have an airplane that's wanting to fly. I can do this in pink. An airplane that's wanting to fly north, straight to the destination. But here I'm going to draw this airplane. If we have this airplane, it's not going to be anything fancy like I said, but I want it to be clear that this is an airplane. So we got this airplane. Just looks a little weird, but bear with me. And if we want to fly straight north, I'm going to rotate this actually. If we wanted to fly straight north, but the wind was blowing us this way, we'd be kind of drifting off to the side. So when we want to go straight north, we want to aim in this direction, and the wind is going to blow us straight north. So the actual airplane, the vector that we're going to draw coming from this airplane, is going to be up here. So this is the plane relative to the wind. This is the wind. And this is the plane relative to the ground. Okay, so bear with me now. This is a sketch with as much information as we need just to imagine, visualize in our heads what this question is really asking. So now we're going to start moving forward here. I'm going to start with our step 1. These steps are going to be the same as previous as previous relative velocity questions we've done in the past. So establish our variables. So we need to establish some variables. We're going to have a P that's going to represent the plane. We're going to have wind, W for wind, and D is going to be for destination. I'm going to write some more information on top of these. So the plane is moving. The wind is also moving. And our destination is stationary. These are just some good properties to associate with our variables, just to keep it all straight in our heads. And the plane is our moving object. The wind is the moving median through which the object is moving. And stationary, well, that's our ground. It's our ground that we define as stationary. So now let's move on to step 2. That is to establish our variables. And when I say establishing variables, what we're talking about is the velocity, the relative velocities. So we're going to need the velocity of the plane relative to the wind. So that's our object relative to the median. The velocity of the wind relative to the destination. And the velocity of the plane relative to the destination. And let's start plugging in the information we know about each of these. So the velocity of the object to the median, that's the first one. The plane relative to the wind. Well, we know the plane will go, imagining that the wind is not moving, we can go a speed of 515 kilometers per hour. So imagining the wind is not moving, the wind is stationary, our plane would be going 515 kilometers per hour. But we do not know the direction. Remember, going back to this graph here, we're looking at the plane relative to the wind, and when we're asking for the direction, it's this angle. We don't know what angle this plane has to fly, what angle this plane has to head. In fact, that's what the question's asking. What will be the plane's direction? So that's our unknown here. So the velocity of the wind relative to the destination, well, that's the velocity of the wind. So 210 kilometers per hour. And we know the direction of that, south 65 east. So south 65 east. And what I want to do here is switch our south and east. We always want our east or west value first. Our east or west value we want in this first position, then our north or south value we want in this second position. So I'm going to write, this is going to be an equivalent vector. It's going to be the exact same thing, just written differently. So east, south. And then for the angle, all we got to do is 90 minus 65 is equal to 25 degrees. So when we flip these values, we get a new angle that's 25 degrees. And then the velocity of the plane relative to the destination. Well, we don't know how fast the plane's going to be going in this pink direction. We don't know this speed. So we're going to just call it VPD. But we do know the direction, and that is north. So the velocity of the plane relative to the destination or the ground, we know the direction but not the magnitude. All right, I'm actually just going to compress this a little bit so that can make space for step 3. Step 3 is to plug in variables. Plug in variables. So we have our equation. What I'm going to do is come up here. Here's our equation for relative velocity. I'm going to copy that down here. So velocity of object relative to the ground equal to the velocity of object relative to the median plus median to ground. And when we are doing, so what we're going to do is rewrite this equation, but with our variables. So the object to ground, well, that is our plane relative to the destination. And then for our object to median, well, that's going to be the plane relative to the wind. And then the wind relative to the destination. And what's important to note here, this is going to be a trick for when you guys are assembling your equations. You see that the velocity, this first object is going to be consistent. When you're looking at this here, this PD, when we're adding our vectors, we're going to have this first value is going to be the first value of our first vector, and the second value is going to be the second value of our second vector. And then in the middle is going to be kind of our third party variable. And you'll see the exact same thing up here, and this will be how you know you got your equation set up properly. When you're looking at these two variables here, you've got the first one and the second one at the very beginning and the very end of your equation. And then the one that's kind of in the middle, your middle one, is going to be consistent as well. So in that order. So let's plug in these values now. So VPD, if we remember VPD, we know the direction is north, is equal to VPW, and VPW, we have the value here, 515 kilometers per hour in some unknown direction, plus VWD. So VWD, we're going to use this one here, kilometers per hour, and the direction was east, 25 south. And what I want to do here, I'm going to make this question mark here, I'm going to make it green, because this is our unknown. If you recall back to the question, we're going to be asked what will be the plane's heading. So this is our unknown. This is going to be the value we're trying to find. So I'm going to keep it green just to help keep it straight. So we're not going to get it confused with our other variables while solving this problem. So let's move on to step 4, to rearrange to isolate unknown. Rearrange to isolate unknown. So remember, our unknown is that green question mark. So we need to rearrange this equation to isolate this term. We're not going to be able to isolate just the direction because this is one term. So we want to isolate this term here. So to do that, we need to bring this to the other side of the equation, and this positive is going to become a negative. So let's write that out here. So what I'm actually going to do is I'm going to bring this to the other side of the equation, and then take this equation and flip it reverse. So you'll see, I'm gonna do this, and hopefully you can all follow along. I'm gonna write 515 kilometers per hour, some unknown direction, is equal to velocity PD, the direction north. And then remember, this is switching sides, so it's going to be a negative 210 kilometers per hour. I want to do this as neatly as I can. The direction east, 25 south. Okay, now there's going to be a few things that we have to do. This here is a negative sign. I'm going to make it red because this is a negative sign we need to get rid of. And to get rid of this negative sign, we need to change this vector. So subtracting this vector is going to be identical to adding the opposite vector. So what's the opposite vector of this? The opposite direction. Well, it's going to be switching the east for west and the south for north. So these two, these are equivalent. These are the exact same thing. Whether you're subtracting this or adding this, it's the same thing. But for our purposes, we need an addition when we're working with vectors. Because the way we subtract vectors is by adding the opposite vector. This is our unknown. So our unknown is still that direction. But the key is, now that we have the form of some vectors in an addition, we can draw a little diagram. We can draw a little diagram to represent this. So I'm going to draw it down here and then move it up top. So we have a VPD north. So some vector north with a length VPD. We don't know what this length is, but that's okay. All we need to know for this vector is that it's headed north. And we add 210 west 25 north. So just going to make this I'm just going to guess the length of this because we don't really have a reference. So let's just say this is about 210. And we're going west and then up 25 degrees towards north. So it's going to be something like this. That's our 210 kilometers per hour. And adding these two vectors gives us our 515. So this is equal to when we add those two vectors, this is our value, our 515. And there's no clean way to draw these overlapping vectors. So you just gotta make the best of what you can, make it as clear and neat as possible. All right. And again, we don't know the direction, so we don't know what this direction is. We don't know what this direction is. This is kind of our unknown. I'm actually going to do it in green for now. This is because this represents our unknown. This green here represents our unknown angle. All right? So what I'm going to do is I'm going to bring this up here. I'm going to copy it, paste it up here so we can continue working. Oops. Bear with me here. I'm going to paste it up here, and this will bring us to step 5. Do the vector triangle. Vector triangle. So we have a vector triangle built. This is the triangle of our vectors, the two that are being added, and the resultant. And now I'm just going to change some of these colors going forward. This angle is going to be purple, and we have some more information. Remember, we know this angle is 25 degrees, and we know that from this vector, this vector here, actually. Sorry, rather this vector here, west 25 north. So this is west, west, west 25 north, meaning that this angle is 90 plus 25 is equal to 115 degrees. So 115 degrees. And that's going to bring us to step 6. Step 6 is going to be to find our angle. So step 6, let's find this angle theta. And to do this, we're going to use the sine law. So say we have a triangle with unknown side lengths C, B, and A. And then we have angles C, angle A, and angle B. Well, the sine law, if you remember, tells us that the sine of A over A is equal to sine B over B, which is equal to sine C over side length C. So this is the sine law. Sine law. And this is what we're going to use to find our angle theta. So let's build this sine law now. So if we have theta, the corresponding side length is going to be the 210. So let's write this. Sine theta over 210 is equal to, and what other angle and side pair do we have? Well, we have this 115 and this 315. So it's equal to sine 115 degrees over the side length of 515. And let's rearrange that to solve for sine theta is equal to sine 115 over 515 multiplied by 210. So the sine of theta is equal to, type this into your calculator with me just to get some practice. I highly recommend following along with your own calculators. You should get a value of 36 or 0.369, 3696, as you can see here. So that tells us that the theta is equal to the sine inverse of 0.3696. So typing this into your calculator, remember to be in degree mode, is equal to 21.69 degrees. And that is our answer. That is our heading. That will be what will be the plane's heading? What direction will the plane point in? Well, this plane we just found is going to point, I'm going to round it to 22 degrees here. 22 degrees. And let's write this out in a statement because we're not quite done yet. I'm going to write the plane's heading. The plane's heading is, well, we got 22 degrees, but there's another piece of that. What direction? Remember our signs here. What direction are we going? Well, according to all these little diagrams we've drawn, the direction we're headed is north 22 east. North 22 towards the west. So let's draw this. Let's write this out. Is 22 degrees, we can write it like this, west of north. Or we could write, since 90 minus 22 is equal to 68, that would be this angle here, 68. We could also write 68 degrees north of west. So we can write 22 degrees west of north, or 68 degrees north of west. So this is west. And just for some more practice, when we want to write this, the square bracket method, this will be north 22 west. So we go north and then 22 degrees towards the west. And in this case, it's going to be west 68 north. So go west, then 68 degrees up towards the north. So it's going to be the same. These are two equivalent ways of writing it. They're all correct. Delete. And then one more note I want to make about these triangles here. You might notice this vector here. This vector here is pointed in this direction. It's 210 kilometers per hour. Whereas this one here is pointed in this direction. They almost look like they're opposites, right? And I just want to explain this a little bit. When we're looking at this one here, this is the reality. This is what we actually observe in real life. The only reason this vector is in the opposite direction, this is kind of an imaginary triangle. This is a triangle that we built just to do some calculations. And the reason that goes in the opposite direction is coming from these steps here, with rearranging the equation and exchanging to be adding the opposite vector. It just so turns out that when we're building our triangle to do our math and our calculations with isolating the unknown, it just so happens that one of our vectors becomes opposite. So just know that this is kind of our imaginary, just theoretical doing our math, whereas in real life, the wind is still acting in this direction. So I just wanted to make that clear. And now going on to the solution visualized, I've kind of summarized the solution here, and know that these values here, they weren't asked for in the question to find the actual speed of the plane relative to the ground, but I've calculated them here anyways. So this VPD and then this angle here, I've calculated them. I'm not gonna really spend too much time on these, but if you want to pause the video and look at what I've done here, you're more than welcome to. But I just wanted to demonstrate what the plane is doing here. So the plane is clearly pointed in the direction of 22 degrees. Sorry, this should not say east, this should say west here. So this is 22 degrees west of north. So our plane is pointed in this direction. And if there were no wind, well, our plane would just fly this way. But because there's a wind, for every 515 kilometers that our plane goes this way, the wind is going to kind of push us to the side and backwards 210 kilometers. So our plane wants to just go this way, but then there's a wind kind of blowing it this way, right? So when you add the two vectors together, our plane just ends up going straight north. What's important to also know, and what I wanted to emphasize here, is that the plane is not pointed north. If the plane were pointed north and the wind kind of blew it this way, our plane would actually be on a trajectory like this. So that's not the case. The plane is actually pointed going off on an angle, but the wind causes it to go straight north towards the destination. I hope this helped, and that is going to be the end of this example. If you want to see more, I've got plenty more posted, but that's all for this video.